Hello, everyone, and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us here today as we talk about multiplying polynomials. Now, in our previous videos, we've already introduced to you what a polynomial is, how polynomials are named based on their degree and their number of terms. We've also talked about putting polynomials into standard form, and then how to simplify polynomials by combining like terms. In addition, we've talked about adding and subtracting polynomials. That brings us to multiplying polynomials. Multiplying polynomials is a fairly new concept for most of our students. There's not a whole lot of familiarity among the students coming into this lesson, so we do spend several days talking about it, and it does have some significant ramifications for us in essentially the rest of Algebra 1 and some very significant implications into Algebra 2 and geometry as well. So we spend a lot of time dealing with multiplication of polynomials. As is typical when we begin talking about something that is very new to our students, that they don't have much familiarity with at all, what I like to do is I like to take you back to something you might already know. For you teachers out there, we call that scaffolding. So I'm going to take you back to 3rd or 4th grade, and we're going to talk about the problem 23 times 8. Now, I am going to assume that most of the people watching this video today understand how to find that solution. What I do want to do, though, is talk you through the process of solving that, because if you're like me and you grew up in a fairly traditional classroom, you probably learned how to multiply using a fairly standard method. Your teacher probably had you take the number 23 times 28 and write it vertically like this and put an equal bar underneath. Once your teacher did that, they probably told you to multiply the 8 times 3, and you knew that 8 times 3 was 24, and they had you put the 4 or 20 and the 4 down, something like this. And then they had you go back, drop a 0, whatever on earth that means, and then they had you multiply the 8 times the 2, which everybody hopefully knows is 16. You lined those up so that your units digits were in the same spot, your tens digits were in the same spot, your hundreds digits were in the same spot, and then you added those together to get 184. Now that's a fairly common way to teach multiplication, but there are some problems with this. It is fairly procedural and simple for elementary school students, so there is some advantage to that, but there's a lot of misconceptions that arise if we teach multiplication this way. For example, when we do the 8 times 3, we wrote 24, and then we dropped a 0. Drop a 0 is not a mathematical principle. It is not a mathematical property. It's just a convention that we use when we're teaching multiplication to children. The problem is that it creates some confusion for the students as to why we would do that and why we're going to multiply the 8 times the 2. A slightly better approach to this focuses a little more on what you were really doing when you were doing the multiplication. And you're going to find that a lot of more modern schools that like to do a more investigative approach, do a much better job of showing multiplication this way. Instead of writing the 23 times 8 in vertical format like we did up here, conceptually we think of this differently. We think of this 23 as being a 20 combined with a 3. That is an addition problem that has an answer of 23, but notice that we've written it so that your ones digit is over here and that your 2 is written out as a 20 because 2 is in the tens place. We've essentially separated our tens digit from our ones digit. Now, that may seem a little more complicated, but notice what happens when I set up the rest of the multiplication problem. Now I say 8 times 3 is 24, just like before, but instead of dropping a 0 and saying 8 times 2 is 16, now I'm doing 8 times 20 is 160. You see, if we teach it this way, what we've done is we have explained why this 0 is here. You see, growing up, I never knew that this 0 was here because I was doing 8 times 20. I simply memorized, drop the 0, and do 8 times 2. Conceptually, this puts your students at a very different place. and we'd still add them together and get 184. You see, conceptually, this helps as we are beginning to think of this process that we learn in pre-algebra. If you have an 8 times a 23, that's the same as 8 times 20 plus 3. In other words, if you have 8 groups of 23, let's call these, I don't know, dollars. If you have 8 piles of $23, you might have 8 piles, and each pile might have a $20 bill and a $3 bill. Now, certainly this isn't the only way to break it up, but it makes sense, a $20 bill and a $3 bill. Because $23 can be made a variety of ways. This way happens to match what I've done over here. And if I have 8 piles of $20 and $3, that's the same as having 8 $20 bills and 8 groups of $3. 8 piles of 20 and 8 threes. Because 8 23s is the same as 8 20s and 8 threes, which is 160 and 24, which is 184. You see, instead of using an algorithm that students memorize to solve this, now we're operating at a conceptual level where the students understand why we're multiplying this way. It's because 8 23s is the same as 8 20s and 8 3s. Hopefully, most of you recognize that what I've really done between this step and this step is the distributive property. It says if you have a certain number of groups, that's the same as having that many of everything in the group. So if I have 8 groups of 23, that's the same as 8 20s and 8 3s. Hopefully that makes sense because that leads us to what we want to talk about with multiplying a polynomial by a monomial. You see, we can do this exact same process, this exact same distributive property, even if the values we're talking about are unknown. You see, instead of a 20 and a 3 here, I have an unknown value and a 7. And I have 5x groups of this. Now, depending on what the x is, these numbers could change. If x was a 4, this would be a 20 and an 11. If x was a 5, this would be a 25 and a 12. It really doesn't matter what x is, because if I have this many of this group, then I have this many of everything in the group. That means I have this many x's, and I have this many 7s. I have 5x x's and I have 5x 7s. The distributive property says whatever's on the outside gets multiplied by everything on the inside. And of course, 5x times x is 5x squared. 5x times 7 is 35x. I do that quickly because I'm hoping that is already familiar to us. If it's not, you're going to want to go back and watch the video on multiplying monomials. And then, of course, I just simplify that and I put it into a box. So it's easy for whoever's grading this to find. That's not overly complicated, right? This is a longer example of the same idea. You could think of this like you would a single-digit number times a 3-digit number. I have this many of this group. That means I have this many 2x's, this many 3y's, and this many 5's. Which I can write out this way. 7x times the 2x, I see my 2 is blue, it should have been green. 7x times 3y, and 7x times the 5. Whatever's on the outside gets distributed to everything on the inside, and then we just compute that. 7x times 2x makes 14x squared. 7x times 3y is 21xy, and 7x times 5 is 35x. And then, of course, I put it in a box so it's easy for whoever's reading it to see and understand. If I were doing this by hand, I probably would have just drawn a box around this, but I wanted you guys to see it without the box and then to show you that it's the final answer, so I did it in 2 steps. You might want to pause the video and try this one on your own. It does look a little bit more complicated, but the principle's still the same. I'm going to assume you've already paused the video and done that, so I'm going to keep going. I'm going to take the 6x squared y, and I'm going to multiply everything in this parentheses by it. That's 6xy times x cubed. This has a minus sign, so I'm bringing that down. This is 6x squared y times 7x squared. and 6x squared y times 11. And when I multiply those together, I get 6x to the 5th y minus, this is 42x to the 4th y, plus this is 66x squared y. And then I put in a pretty box for you. Here's one more. Try that on your own. I'm going to assume you've already done that. We'll do this one a little more quickly. Whatever's on the outside gets multiplied by everything on the inside. Be very careful because you've got a negative here and a minus here. When I multiply this together, I get negative 18x to the 7th y to the 3rd. This minus negative becomes minus negative 16x squared y to the 3rd, which turns into plus positive. Notice this is a typo right here. This should be an x to the 4th. I missed that one. Just be aware because I did correct it down here. Not overly complex, right? Not too bad. I can take these same principles and I can apply them to polynomials as well. I can apply them to polynomials as well. Just like in elementary school, your teacher would have you solve a problem like 36 times 28 this way. 36 times 28, you write them vertically, put your equals bar. Your teacher would have you take 8 times 6 is 48, and you'd write the 8 and carry the 4. Whatever carrying the 4 means, who knows. Then your teacher would have you do 8 times 3 is, let's get my cursor up here, 8 times 3 is 24, add the 4, no one has any idea why, to get 28, and you end up with 288. Then you've got that drop the 0 that nobody really understands, and then you're going to take your 2. 2 times 6 is 12. Once again, you're going to put your 2 and you're going to carry the 1, whatever that means. And you're going to do 2 times 3 is 6. Add the 1, for some reason nobody understands, and get 7. And just like before, you add those together. Again, this is probably how you learned this growing up in the classroom, unless your teacher was a little more current. This is not a great approach. Again, it's very efficient, and it does give a procedure that small children can follow without too much struggle, but conceptually you lose a lot. So just like before, I'm going to take these numbers and I'm going to split them. Let's take the 36 and rewrite it as a 30 plus 6. And let's take the 28 and write it as a 20 plus 8, and now we're going to do the same thing. Notice what happens. We get 8 times 6 is 48. Well, that makes sense to me. 8 times 30 is 240. Okay, that explains why this 0 is here. I'm going to take the 20 times the 6 and get 120. And then lastly, I'm going to take my 20 times my 30 and get 600. I add all those together, and I get the exact same solution I got up here. Notice this is more steps than this is, but conceptually it should make more sense. If I have 8 36s, that's 8 6s and 8 30s. If I have 20 36s, that's 26s and 20 30s. In fact, this leads us to an idea we learn in pre-algebra that says, if I have 36 times 28, that's 36 20 plus 8s. This is just addition. I split it out so you could see them both. That's 36 20s and 36 8s. That's the distributive property. 36 of a group means 36 of everything in the group. I'm going to focus just over here for just a moment. 36 times 20, because that's some fairly complicated multiplication. I'm going to break that up, and I'm going to do it over here as well. I'm going to take that 36 times 20, which is complicated, and I'm going to break that 36 into a 30 and a 6. And I'm going to do the same thing over here, 30 and a 6. I do that because 30 times 20 is easy to multiply. So I use the distributive property. I have 20 of this group. That's 20 of everything in the group. That's 20 30s and 20 6s. Same thing over here. If I split that 36 into 30 and 6, that means I have 8 groups of 30 and 6. That's 8 30s and 8 6s. And I can multiply those together. 30 times 20 is 600, 6 times 20 is 120, 30 times 8 is 240, 6 times 8 is 48, which adds up to be the same thing as the other two methods. Now, I'm not so naive to believe that this wasn't really convoluted and a little bit confusing. That's okay. Just remember, you're splitting these so that the tens digit and the ones digit are separate, and then you're using your distributive property. Then you're coming down here and doing the same thing with the 36. But there's something cool I want you to pick up on. Notice what happens at the end. The 8 gets multiplied by the 6, that's here. The 8 gets multiplied by the 30, that's here. The 20 gets multiplied by the 6, which is right here. The 20 gets multiplied by the 30, which is here. This right here is the exact same thing as this over here. It's just written in a little more algebraic fashion. Now, why am I doing all of this? This is actually very, very cool. Notice I have a linear binomial x plus 5 times a linear binomial x plus 8. And I want to multiply those two things together. I can think of this the exact same way we did 36 and 28. And that is, I can think of this as, let me switch to a pen real quick. I can think of this as 30 plus 6, wow, that's messy, being multiplied by 20 plus 8. Can you see how the structure here is the same as the structure here? You have an addition problem and an addition problem, and then you have their solutions multiplied together. I'm going to take this and do the exact same thing we did right here. In that, I'm going to go through and I'm going to multiply this x times everything in the second parentheses, and then I'm going to take this 5 and multiply it by everything in this parentheses. Just like down here, I took 8 times both and 20 times both. I'm going to do the same thing with this. Here's what that looks like. I take the x times the x, plus I take the x times the 8. Notice the x got multiplied by both the terms in the second parentheses. Plus, I'm now going to take this 5 and multiply it by everything in the parentheses. That's the 5 times the x plus the 5 times the 8. It's essentially the same thing you just did right here. Notice what I did is I took the first item in each parentheses and multiplied it together. I then took the first item and the last item and multiplied them together. Notice those are on the outside edges. I then took the 5 times the x, which are the things that are closest together. We sometimes refer to those as the inside. And then I took the 5 times the 8, or the last item in each set of parentheses. Notice that creates an acronym FOIL, the FOIL method. If you've heard of the FOIL method, this is what they're talking about. It's how you multiply a binomial times a binomial. Now, I personally am not a big fan of this acronym, and I'll show you why in just a second. Part of it stems from the same reason that I don't like multiplying this way, is I think that if you memorize this, you can get the right answer, but you don't truly understand what's really going on, and that is the application of the distributive property. Either way, whether you use the acronym or not, we know that x times x makes x squared right here. We know that 8 times x makes 8x. We know that 5 times x is 5x, and we know that 5 times 8 makes 40. Notice these middle numbers right here are like terms, so we're going to combine those and get x squared plus 13x plus 40. If we were to multiply this times this, or I should say this times this would be the outcome. Now, I don't really have time to do it in the video, but if you have the urge and you're not quite convinced, you can make it up a number and stick it in for x, and then you simplify this using order of operations. You can stick that same number in here and simplify using order of operations, and it will come out. I want to try another one of these. We'll do this one a little more quickly. Once again, I'm going to take the first item in each set of parentheses. That's the x and the x. I'm going to multiply those together. Plus, I'm going to take that x times the 13, the outside terms, and multiply those together. I'm going to take the 10 and the x, and I'm going to take the 10 and the 13. Notice the 10 and the x are the inside terms, the 10 and the 13 are the last terms in each set of parentheses. And then I'm just going to simplify x times x, 13 times x, 10 times x, and 10 times 13, and I get this. Once again, my middle terms are the same. You're going to find that happens a lot. I get x squared plus 23x plus 130. Not too bad, right? Tell you what, here's a couple different examples of that. I would urge you to pause the video, try one, then watch the video to see how it's done, make sure you did it right, and do the same thing through each of these. I'm going to go through these relatively quickly because these are just extra practice examples for you. Notice the first example, you're taking the first items, x times x, plus x times the negative 7, plus 3 times the x, plus 3 times the negative 7. And when you simplify that, it's x squared minus 7x plus 3x plus negative 21, which then is x squared minus 4x minus 21. The next example, you multiply the x's together. That's the first item in each set of parentheses. Plus, you're going to multiply the outside terms, the x and the negative 4, the inside terms, the last terms. You simplify each of those, combine those like terms in the middle. 2x times x, 2x times 5, negative 3 times x, negative 3 times 5. Well, that's 2x squared plus 10x plus negative 3x plus negative 15, which gives you 2, oops, little typo there, 2x squared plus 7x minus 15. Last one, 3m times 4m. 3m times negative 1, negative 6 times 4m, negative 6 times negative 1, gives you 12m squared minus 3m minus 24m plus 6, and you combine the like terms in the middle. Not too bad if you just remember that it's the distributive property. Everything in the first gets multiplied by everything in the second. Now, if we'd been doing this by hand, I would have gone through and I would have drawn arrows every single time like I did on that first example. I find that that's a little bit difficult to do on the computer, so I skipped over that. However, that is a good suggestion for helping you keep your thoughts organized. One more thing. One of the reasons I don't like the FOIL method name is because when I try and do larger polynomials, like this linear binomial times this quadratic trinomial, the FOIL method really doesn't make as much sense. But if we just remember the distributive property, how everything in the first gets multiplied by everything in the second, then it makes a whole lot more sense. I'm going to do x times x squared. I'm going to do the x times the negative 3x. I'm going to do the x times the negative 2. Plus, I'm going to do the 5 times the x squared, the 5 times the negative 3x, and the 5 times the negative 2. X times x squared is x cubed. X times negative 3x is negative 3x squared. X times negative 2 is negative 2x. 5 times x squared is 5x squared. 5 times negative 3x is negative 15x. And 5 times negative 2 is negative 10. Now, just like before, I'm going to go through and combine my like terms. However, it's important to realize that there's a whole lot more of them this time, so we've got to be much more careful. Take a look here. This is my highest degree term, so I'm going to put it first. It is the only x to the third, so I'm just going to leave it alone. I then notice that I have a negative 3x squared and a positive 5x squared, which makes positive 2x squared. I have a negative 2x and a negative 15x, which is a negative 17x. And then I've got this little negative 10 on the end, there is your solution. I did not go through and put a nice box around that this time. I hope you'll forgive me for that. Make sure that if you have a plus negative, if you're uncomfortable with that, make sure you do take the time to go ahead and turn that back into a minus sign. Really doesn't matter a whole lot, but it makes it look a little nicer. Here's a second one. One more time, I would encourage you to pause and try this on your own. Again, I have color-coded it for you. Hopefully that will help you as you're working your way through. It is kind of disappointing that the textbooks aren't color-coded, but you know, when you're working on these, once you get used to them, it is much less of a factor. I'm going to do this quickly, assuming you've paused and tried on your own. Multiply the x times everything in the first, or everything in the second parentheses. Take the negative 3 times everything. Simplify each of those expressions. And start looking for things that are alike. And there's your solution. Just like before, I did take that plus negative 10 and write it as a minus 10. That just felt a little nicer to me. You're welcome to do that or not. It really isn't going to make a huge difference, although it may be helpful for you in the next unit as well. Hopefully that made a whole lot of sense to you. If not, take a second, go back and watch that again, particularly the beginning parts on how we actually do multiplication with two-digit numbers. I think that will be very informative. Again, if you're having trouble with the multiplication of the monomials times the monomials, there is a separate video for that. I didn't spend a lot of time on it here, but you may want to go back and look that over as well. As always, we do appreciate you taking the time to join us here today. Make sure you leave us a comment in the comment section. Make sure you like and subscribe, and certainly turn on those notifications so you don't miss anything coming out of Nunley Math. You guys take care of yourself. Thank you so much. Bye-bye.